Hey, welcome everyone to the Trusted Autonomous Systems seminar series. For those who haven't met me, I'm Dr. Simon Ng. I'm the Chief Engineer for the Trusted Autonomous Systems Defence CRC, and it's my pleasure to host you here this evening or this morning or today, wherever you are. Many of you will be familiar with the centre. But for those who aren't, we're a not-for-profit private company funded by Defence and the Queensland State Government, and we're working to create asymmetric advantage for defence and strengthen sovereign industry through targeted development of trusted autonomous systems. I might just ask people who are joining to make sure you're muted. I'm getting a bit of background noise coming through. Thanks, guys. We have an extensive program in the Centre investigating and developing approaches for the regulation and assurance of autonomy as part of achieving that trust in autonomous systems. And this seminar is actually contributing to the broader dialogue in this area. It's the second seminar provided by Dr. Mark Nicholson, our guest speaker from the University of York's Assurance of Autonomy International Program. Can I just ask everybody to mute their microphones, please? Sorry about that. So today, Dr. Nicholson will provide a seminar on assurance of machine learning for use in autonomous systems, or AMLAS. And then, if time permits, we'll play a video showing AMLAS being applied to the assurance of an autonomous driving system. Feel free to ask questions using the chat. I think you can raise your hands in this particular software, so you can raise your hands. Mark, you're keen to have questions asked as they arise. You don't want anything too formal, is that right?
Yeah, that's great. That's fine by me. Throw them at me and we'll see what happens.
Excellent. When you aren't speaking, as I've said, please mute your microphone. This is being recorded, so I don't want to capture a lot of background noise in the recording. The recording will be made public, so just be aware of that. Anything you say will be put up on our public website. There will be some material put in the chat room by Tom Putland, our Director of Autonomy Accreditation AIR, including a link to both the presentation and the video example that's being applied to the autonomous driving system. Just for a little bit of background, Mark is a dedicated researcher and educator with 30 years of experience in safety critical systems engineering. He's provided consultancy to a number of organisations, and he is the education lead at the AAIP, also the director of Safety Critical Systems Club. Sounds like the coolest club you can belong to, Mark. The UK's professional network for sharing knowledge about safety critical systems. Research interests include the concept of data safety and how to embed this concept within current safety processes and practices and future robotics and autonomous systems. So with that, I will hand over to you, Mark, if you can bring up your presentation, and I will give you the mic.
Okay, well, thank you very much for that. It all sounds quite exciting when you spell it out there. Okay, so let's get started with my talk on assuring safety of machine learning, particularly in the context of autonomous systems. I'm going to start by making two assumptions. The first assumption is that you're currently using best practice systems engineering processes to develop a safety critical system, such as an aircraft or whatever. And secondly, that you're using best practice system safety engineering processes associated with that systems engineering, so that when you release a system to service, you've got evidence of the safety characteristics of that system, and usually you've got certification associated with it. So now you want to move on to generating autonomous systems and putting those out into the wild. And as part of that, you want to use machine learning components within those autonomous systems. The only problem is that that disrupts both systems engineering and system safety engineering practices. That was exciting. I got muted there, so I've unmuted myself. So as I was saying, autonomy and machine learning actually disrupts those systems and system safety engineering processes. How does that actually work? Well, let's look at, if you will do it, there we go. Let's look at a standard V lifecycle model for the development of a system. We're putting in autonomous capability, and we're going to do system safety processes associated with that. The problem here is there's two main extra challenges we have to address. The first one is we're moving to a much more open environment. We're operating on public roads, we're operating in hospital or care settings, and that actually means we've got to cope with a lot more of environmental activity than we currently do in a much wider range of scenarios. And somehow our safety processes have to assure that. Also, of course, we're moving on to make machines make decisions that normally would be the parlance of a human being. So we've got to ensure the safety of both of those elements, and we've got to make sure that we can undertake those appropriately. One of the ways in which we do that is to use machine learning components. So we're building a system component that can do work for us within that new operating activity in the new operating environment using machine learning. And we want to make sure that the contribution of that machine learning component to the safety characteristics of the overall system is acceptably safe. AMLAS, which looks at that element of how machine learning contributes to the safety characteristics of the overall system, currently assumes that you're employing supervised learning. It does this because most of the elements that are getting very close to operation out there in the real world, your automatic lane keeping functions and things like that, are currently using supervised learning, usually around classification problems. Now, there's no reason why you can't expand this from this assumption, but that's where we are at the moment. And then we also assume that we're going to take that final model developed from your data and fix that at operational time by deploying it as software. Of course, you can always go around and relearn by doing a new round of supervised learning. So that's the context. We're moving into autonomous systems. To make those autonomous systems have the capabilities we need, we're going to use machine learning. So here's my development process on the left-hand side with appropriate safety activities. This is actually a diagram from ARP 4754A, which is the current acceptable means of compliance for large aircraft. And it's a requirements-based process. You identify a set of requirements, you develop an architecture to meet those requirements. Some of those requirements will be safety requirements. You decompose those requirements down, and eventually you get to hardware and software components. Now you're moving into machine learning components. And here, this is where we have to plug in a new workflow. So we need to plug in now a machine learning workflow, and we need to assure the properties of that machine learning workflow for its safety characteristics, so that we can show that we've met the safety requirements that we've got on that process. So here's our model of the machine learning workflow that we've used as part of AMLAS. So we've assumed that, of course, we've got to collect the appropriate data, and we've got to persuade ourselves that we've got good data. We then employ a supervised machine learning over that data to produce ourselves a best model for whatever the classification problem or equivalent that we're undertaking. And then we verify that model, deploy that model back into the system, run it for a while in the real world, so in an operational safety system, build up understanding of how well that's working, and then as necessary, updating the data and running around that work life cycle again. And of course, if we want to put this system out into operation, we have to have good safety properties being embedded in the system for the machine learning component, that it's learnt the right things at the right time and therefore doesn't contribute inappropriately to safety. So we have autonomous systems, we have machine learning components that are going to contribute to that. Overall,
there's a question in the chat there, or
yeah.
Tom, did you want to ask or make a comment?
Oh, no, we can, as when Muffy was up to it, to answer that one, I was more just to leave it in there while I had it at my front of my mind. But it was on ensuring coverage of feature spaces to make sure that you deal with false positives and false negatives adequately, especially when measuring performance.
Absolutely, and you're absolutely right. That's part of the decomposition. I'll come back to that in a second, but you're absolutely right. One of the things that we have to specify as part of the verification process, but also as part of the safety requirement, is what the appropriate features are and what good coverage looks like over those. And there's certainly quite a bit of work going on at the moment about how you actually identify what feature coverage looks like. We've done that pretty well now, I think, for data, and I'll talk about 4 characteristics of data over for that. But the actual features of the model, that's still an ongoing challenge. Even whether the concept of coverage is quite right for these circumstances is still open for debate. And we certainly got a couple of papers on that from the AAIP, which I can always point people to afterwards.
Mark, there's also a question from Damien Copeland. How do you determine the safety standard you want the machine learning to achieve?
How do you
determine the safety standard you want the machine learning to achieve?
Okay, yes, absolutely. Well, that's part of the flow down from the systems level. So you have a safety requirements flowing down from the system level to you, and you're going to have to translate that into what those requirements are over the machine learning. And we know, for instance, that if you start putting the catastrophic requirements for software onto the machine learning, so we've got a catastrophic event, 1 × 10⁻⁹ per average operating hour, FDAL-A if you're in civil aerospace, trying to claim that you've got 10⁻⁹ of machine learning isn't going to work. So the architecture has to bring that down to an appropriate level. You then have to translate that into what that means at the machine learning level. And that's an explicit part of the AMLAS process, how you do that. Now, what an acceptable level of safety for autonomous systems is, as far as the public is concerned, the standards that will get placed on it is still an open area of research. We're talking extensively with the regulators on this, because the decision-making changes the nature of the requirements that we're going to end up placing on it, and that will then flow down. But that's an explicit part of the translation that you have to do from the system safety requirement into the specifics of the machine learning requirements, and that's part of the AMLAS process.
Thanks, Mark. Please continue.
Right, so okay, so we have our system that we're proposing. and we want to put it out into the real world, release it to service. And typically that means we have to develop a safety case, an assurance case, or equivalent. And just to bring remind us what a safety case is, it's a reasoned and compelling argument supported by a body of evidence that whatever the system is, in this case an autonomous system or service, will operate safely for a defined application in a defined environment. So you might want to show that your automatic lane keeping system using machine learning is acceptably safe within your level 4 autonomous vehicle operating in Australian conditions, for instance. Now, if you'll notice, that has two elements to it. It has to have an argument. So you have to give us some story as to why we should believe you, that you've set appropriate requirements on the ML and that you've developed to and met those requirements. And you also have to provide the evidence to back that up. So we have a story to tell, and we've got here one sort of classic story that gets told in a safety case, and we've got evidence that backs that up. And as you'll see here in blue, we've got the scope of the system, the description, the hazards, the safety requirements, and we've decomposed those down and made control and risk reduction measures over those, assessed the risk. We've got a justification for the development process and how that's appropriate and proportionate, and we're saying something about how we're going to make sure it remains safe in operation through the safety management system. Now, these can get quite chunky. You can do them in text, and people regularly do, but you can also represent them graphically. And there are a number of different graphical representation techniques. The ones that we've used here for AMLAS to give you a pattern to work to is representing something called the goal structuring notation. It looks a bit weird and wonderful when you get it to look at for the first time, but actually there's only really 5 symbols being used. And then arrowed lines between them, I guess, is the 6th. So you've got some sort of goal that you want to meet with respect to safety. So I've got this automatic lane keeping system is acceptably safe to operate on the public roads in Australia. You've got some evidence that you've produced over the features or other characteristics of that system that you're going to help, is going to back up your argument for safety. You've got strategies which are ways of breaking that down. So historically for civil aircraft, for instance, we break them down by looking at the safety characteristics of each of the functions. So you get from a higher level goal, you break that down via a strategy to lower level goals. You break those down again and again and again until you get to a point where you can provide some evidence against those. And we also have things called contexts, which actually give you some information about the scenario in which that safety argument holds. So I just wanted to give you that because in AMLAS, all of our patterns of how you actually undertake this are against, are represented in this goal structuring notation. You could use any one you like of those representational forms. We happen to use goal structuring notation, partly because it happened to be developed in York originally. And there are standards for how that works. So where are we now? Well, we're trying to develop a system, an autonomous system with certain capabilities. As part of that, we have machine learning components. We want to persuade ourselves and other people that the contribution to safety of that machine learning component is appropriate, is acceptable. It meets the safety requirements that are set on it, and therefore it contributes well to that overall safety case. And that is the contribution that AMLAS is going to provide for us. So it's going to provide us argument and evidence into the safety case for the system. So that's putting it all into context. Machine learning is not safe or unsafe in itself. It only has safety properties in the context in which it's being operated. So we've developed a process, a workflow for you, and associated with that workflow, you produce pieces of evidence and you fill in, using that evidence, argument structures. So as you can see here, we've got a set of safety requirements coming into you from the system level, into your ML component. You then make sure you understand that component in the first element, which is the safety assurance scoping. You then from that put requirements onto your machine learning model development, and you track those and build those up and assure those, make sure they're valid as you go through the development of your model. Once you've got the model, you verify it, and that's step 5. And then, of course, you have to fit it in. So verification is at the end there, I guess there. And then, of course, you have to fit it into the actual system. So you have to deploy it. And I've got 2 more in here, which are the data management assurance and the model learning assurance. And what they're looking at is the quality of the model you produce is a factor of both the data that you use to to seed that model and the actual learning process that you employed. So we want to argue that the end model that you're using is appropriate because you set it up to meet its requirements, which meet the safety requirements overall of the system. You've got good data, you've got good model learning, you've verified the final output, you've made sure that you integrate it properly into the system so that it meets its system safety requirements. And because this is during development time, you have a feedback loop going backwards and forwards across these elements.
Mark, a couple more questions, if you don't mind.
Yep. Yeah.
Tanya Dixit has asked a question: how do you make sure all the possible testing scenarios are considered? And I guess this relates back to the feature space question as well in a different way.
The answer is you probably can't. So the question is, how much uncertainty have you, how much evidence does that set of tests that you've given, you've taken, give you against the safety requirements that are placed on that ML component? So it's completeness is very difficult to argue, very difficult to provide evidence against with confidence. So you have to ask yourself how hard I've looked for these things, what argument I've got that I've got an appropriate set of test cases and edge cases. Have I also set up monitoring so I can find new edge cases quickly in the operational sphere? And I think that's very important for autonomous systems, because it's very difficult, as far as I can tell, to claim completeness here. And then also asking yourself, is there any alternative ways in the architecture to overcome biodiversity or redundancy any failure in that ML against its safety requirements? So you're putting it back into the safety space. So I think it's very difficult to claim complete coverage. What you're trying to do is to show that you've put appropriate evidence, appropriate effort into that.
Thanks, thanks, Mark. I've got another question from Kate Devitt, which is quite complicated.
So can somebody turn off their? Thank you.
I've just done it. I've got a question from Kate. It's quite a long question. You can see in the chat, but I'll just ask the first part of it. Is it possible that the story that does a good job in justifying future machine learning system safety is too complex for humans to comprehend?
I think at one level of abstraction, no. The top level story, I think we can put it together in a way that we can explain it to ourselves and other stakeholders. The detail of that into the modelling, that's really quite, that's a different story, and there may be only a set of competent people that are able to understand that. And you're right, you may be starting to talk about some automated judgment around that, and that is the whole thing that explainability is starting to look at the moment, and trying to understand how much of this and what the nature of that should be to the humans, either assuring that process as experts, but also, of course, stakeholders who are going to use it in the real world and understand enough about it to have confidence and trust it appropriately. And we've been doing quite a bit of work at the moment on looking at what potential buyers of autonomous vehicles believe about these sorts of things, and what they will and will not trust. And they come into very clearly two camps. They're either very, very trusting, or rapidly become very trusting, or they're very skeptical and sort of remain skeptical. And that's going to be a big challenge for us, because it's different stakeholders needing different outcomes to that. But yeah, it's going to be a real challenge.
Thanks, Mark. Please continue.
Right, okay, then. So let me just go through each of these elements one at a time. But the first thing I'd say is that each of them talks about, as you're developing your machine learning, to provide the model that you're going to use as part of a classification problem or whatever, that you should log the activities you've done, the development actions, the decisions that you've made. So for instance, here I've just given one of them about the ML development log. And there it states that you shall document and justify all the key decisions made during the learning process, and how those choices impact performance or robustness of the final model. And by robustness, I mean its ability to cope with subtly different scenarios to what it was trained on, and still come up with good results. And here you can see the examples I've given you around what tool chain have you used, what sort of model, what sort of parameters, what the classification threshold levels have been, etc., how you've dealt with these sorts of things. So suppose we have a safety requirement coming down to us from the system level. So we've got an autonomous driving application here, which has got a subsystem required to identify pedestrians at a crossing. A component within the perception pipeline is being asked to undertake a requirement of the form. When ego is 50 meters from the crossing, the object detection component shall identify pedestrians that are on or close to the crossing in their correct position. So you've got a safety requirement to do that as part of your not hitting pedestrians on a level crossing. And you're going to do that in ML, and you want to assure yourself of that. So the first step in the AMLAS process is called safety assurance scoping. And there we've got a number of input documents. So typically when we see these AMLAS, we'll have documents represented here that are coming into this part of the process. We'll have workflow activities here identified in orange. So we're going to define the assurance scope for the ML component, put it into its system context, in other words. And from that, we will get an output of the safety requirements allocated to this particular component so that we can do traceability. And we're going to give you a piece of argument and back evidence that that bit of the process has worked well. So we have workflow items, we have documentation in and out of this bit of the process. And from that, you can fill in the appropriate piece of goal structuring notation argument. So the argument here, which is the overall argument for an ML component, is that the ML component satisfies its allocated system safety requirements in the defined environment. So you're putting this component into an appropriate context. And here you can see how we've taken the documentation and incorporated it here mainly as context. And probably the most important of those contexts is E. And E talks about the system safety requirements allocated to the ML components. Now, these are very important, of course, because you're then going to develop your ML component against those. You're going to verify it against those requirements. And why is this particularly important? And this comes back to the question around how this links into safety. Well, if you think about it, there's a chain going on here. We've got machine learning as the component that produces a model. If there are characteristics of that model that are not correct within the system context, it would lead to essentially a software failure. So, for instance, if a false negative, I don't have a person on that level crossing, you may want to put targets onto that particular element. You may want to, in other circumstances, put it onto the false positives. You may want to put it onto any element of the confusion matrix, and you can put targets on that and say we need to push those down because of the contribution that those particular deficiencies, failures, attributes of the final machine learning model need to be within a certain parameters, so that we can make an argument that the risk of those machine learning failures against the classification task or whatever it is, against a pedestrian level crossing, means that that isn't a contributor to a hazard and therefore an accident. So, it isn't a matter that your machine learning has to be perfect. Guess what? It won't be. What it is trying to identify against safety concerns, against your safe operating concept, what types of failure in that machine learning would actually contribute to, and how to get what the targets on that should be. So we're putting it into that whole system perspective. So we've got our system level safety requirements, we're translating those into machine learning components. So we now need to think about the requirements of those, which is step 2. Develop and validate those machine learning safety requirements that have come from the allocated system safety requirements. That's not a trivial task at the moment, because these are very new and novel components for us in a system safety context. So we've got the safety requirements coming in, we've got 3 work activities here: develop those safety requirements, validate those requirements, provide evidence against that. And from that, you will get documents, and you will need to fill in the evidence in the bit of safety argument that says you've done that well, and that therefore, if your ML meets those requirements on it, it will contribute well into the overall system safety. So here we have our little bit of safety case associated with that, and you'll notice here that we've got a breakdown which essentially has 2 elements to it. We've got G 2.2 and there's a G 2.3 over the other side. Do that. There. So there we've got the ML safety requirements are valid development of the system, allocated system safety requirements, and you've got a rationale for what the validation process you used and why you believe it's good. And then you've got the key one, which is the ML model satisfies the ML safety requirements, which is that G2.2. Now, part of the argument for why you should believe that is true is that the ML model was based on good data, and it was based on a good learning process as well. And I've identified those two here because they're the subjects of the next two elements. Because if you don't have good data coming in, you're not going to get a good model. Even if you've got good data coming in, but a poor model learning, machine learning activity, you're going to have poor end result from that. And you want to assure yourself of that. So the next step is a workflow items relating to the generation validation of the data that you're going to use, the data sets that you're using to develop that ML component. And of course, you'll have a separate independent set for verification as well. So we've got workflow. We've got the define the data requirements based on the safety requirements, generate the data, validate the data, and then instantiate that machine learning data argument. I'll talk about it in a second. From that, you get a set of documents which identify the data requirements, how you're going to develop the data, how you're going to internally test the data, verification data, and what decisions you made while you did that in the log, etc. So the important feature there is that you're now making an argument that the data used to develop and verify your machine learning model is sufficient data to do that within the context of the system you intend to place that ML component and the safety requirements placed on it. And we've identified 4 core requirements relating to that. We've got relevance, so the data should be relevant to the situation. The data should be complete, and we'll need you to argue and provide evidence for the completeness of it, that it's accurate data to an appropriate level of accuracy as required against the features that you want. And if you notice in that ego, it had a requirement, it had that at 50 meters, you must be able to identify. So that will set a accuracy on the data, on the placement of where that human is in the environment. And it should be balanced. That's a slightly tricky one to get your head around, but essentially it says the data should represent the characteristics of the environment it's working over. So if you're doing something over a population and 50% of the population are male and 50% are female, but your data set has only 20% male and 80% female in it, then it's not balanced. If it was a 20-80 mix in there and you did 50-50, you need a balance of the data that you're getting against the situation that the model's got to learn over. And of course, in order to make sure you've got that, you may have to undertake a number of activities. You may, for instance, have to do data augmentation, either by going out and collecting more information or by synthesis or whatever. And eventually, whatever you've done, you've got to make a judgment against those elements and persuade yourself that those 4 are good, and that you've got the appropriate evidence to show that.
Mark, just letting you know, we've got about 20 minutes to go.
Yeah.
We can, of course, we will insert a link to the video into the chat for people to access.
Yeah, brilliant. So any more questions at the moment?
Yes, another one from Tanya Dixit. Do you think reproducibility tracking of experiments should be planned from the start of a critical project like autonomous systems? How important is it?
Yes, absolutely. Yes, absolutely I do. And in fact, in general, I think one of the things you need to do in order to populate these logs in order to think and make sure you've got the right data is to have an information management plan up front. That gets particularly important when you start doing trials and things like that, because you've got your components in the actual vehicle, in the actual operating environment. If you try to collect every single piece of data that an autonomous vehicle could generate, you're just going to drown in data. So you have to work out what's appropriate to collect, and you have to have a management plan for that. And some of the interesting features of that is, of course, you may not own some of that data. So there's all sorts of issues about the management of data over this process. But yes, absolutely. Trying to understand how you can reproduce this is part of the confidence element in there.
Please proceed.
Right, okay. So we've got a set of requirements. We've assured those requirements. We've got good data coming in. We're now going to produce a model an ML component with an appropriate model in it. Of course, we've now got to assure ourselves of the ML learning process itself. So we're going to create the machine learning model. We're going to test that model. And obviously coming into that, we've got our safety requirements, we've got our development data, we've got our test data suite, which of course will be different from. And from that, we can build up evidence about how well that machine learning process has worked. So this is a process argument, so that we can have process evidence around the quality of the outcome of the model that we've generated. And once again here, we can identify an appropriate model for that. And we've got under 4.2 selected model, which is this one here. We've got the selected model satisfies the machine learning safety requirements using its internal tester data. And then the development approach adopted to create the model is sufficient. And of course, there you're talking over the type of model, the model parameters, the model development process, and why those shouldn't have introduced errors into the final ML model, so that you can make an argument that we don't have deficiencies introduced in the final model as part of the development process. So the overall argument you're trying to do there is that the development of the learned model is sufficient in the context. And of course, the more stringent the safety requirements, the higher the level of potential impact, the more stringent you will be over that. So the next one, you've now got a model. You've got the final ML model that you want to put into operation, or it's the version at the moment you've got, and you want to show that that will meet the safety requirements. Now, for that, of course, you need verification data. And there's lots and lots and lots of work been going on at York and other places about how you generate appropriate verification data. They tend to fall into two camps. And so our safety argument talks about you can either use testing data. So the ML safety requirement is satisfied using verification data. So that's essentially over testing and simulation. So this little symbol, which is an extra one I didn't represent earlier, says you can do either or both of these. You can use formal verification techniques if that's the approach that you think is appropriate. So you can do formal verification, you can do testing. Of course, you've got to make sure that that testing verification is not using the initial data set, because it's confirming itself. And so we've got another little argument up here that says that the data used is suitably independent of the data that was used to create the model in the first place. So that's around the verification, and pick your best verification techniques that you believe are appropriate within that context, and try and persuade us that's done the good work. And then finally, you've now got a model that you believe meets those safety requirements. You've verified that model. You now have to integrate it back into the system. So you now have to put it back into that system as part of the safety, as part of that element, and then you have to do assurance at that system level. So it will then go back up to the next level out. So you have to integrate the machine learning model. You have to test the integration in that, and you can do simulation, you can do trials or whatever against the operational scenarios, and that comes back to the question, the range of those operational scenarios that you need in the context that you've got, and a justification for that, all those edge cases, etc. And then you're instantiating the appropriate safety argument to persuade yourselves and other people of that. So the workflow is integrating that component and demonstrating that the allocated system safety requirements are now satisfied during operation of the target system in its environment. So here's the final bit of argument pattern in there. And once again, that's broken down into two elements, there and there. So allocated system safety requirements are satisfied under all defined operating scenarios when the ML component is integrated. That's that one. And we want to provide evidence for that. That's integration testing. And all these allocated system safety requirements are satisfied throughout systems operation. So you're going to put a monitoring regime into place in there so that you can identify any gaps, any errors in the ML model, that you can then go back around a learning process and an upgrade of that model really quickly before an accident occurs, and you can make an argument about that. And I think in comparison to modern current systems, we're just not going to get to the level of assurance purely at development. The baseline that we put out is not going to be assured to the level that we currently are used to, at least for the foreseeable future. And we're going to rely very much on looking at that in operation and doing a very fast turnaround for an update and a rebaseline. And that's where all the discussions around dynamic safety cases and things like that comes from. So overall, we've set a framework for you, which has got a set of work activities. And as you can see, we've identified 17 work activities that generates and consumes a number of documents. And from that, for any machine learning component, you can generate a safety case. And we've given you a pattern for that. And here you can see the color coding against the workflow elements that I've identified previously. The AMLAS Handbook is now at version 1.2. It's available free. It gives you a lot more examples and notes. There is also a significant amount of work going on at the moment to produce 2 or 3 very large examples of the AMLAS in operation, particularly in the medical domain in the UK and the automotive domain. So I recommend that you go and have a download of the document. It'll be the latest version. I've got version 1 here from this year, February, but it's up to version 1.2 now, and we're updating it as we get more evidence back. And I've just given you the link here to go and look at. And here's just a thanks to the numerous people that were part of that process. And there's many, many more now trying to use it in practice. So that was the point at which I was going to give the example that Colin created a video for me. I thought this might overrun, so I'm quite happy for that to be, for you to look at that separately. So the conclusions are, it's currently a technique of choice for a variety of classification problems in multiple domains. A number of those have safety properties associated with it. As well as meeting the performance requirements on it, we have to address safety risk, and we have to provide a safety assurance over that risk. And so we have to be able to produce argument and evidence in the form of the contribution of that ML to the overall safety case for that particular system in that operating environment. And we can't give you a case-by-case basis, so we're giving you a structure by which you can do that. And so at that point, I will stop sharing, so that then we can add any last questions.
Fantastic, thanks, Mark. So there are a couple more questions. There's one from Tom Putland, which I'm just going to paraphrase. Can you speak to the role of synthetic environments and maybe some of the risks of synthetic environments as well in the process that you've outlined?
Yes, absolutely. Historically, we gave very static scenarios to a system and showed that the results of those were what we wanted to happen. Of course, as we get into a decision-making process, we're going to have to show that a dynamic sequence of actions that is undertaking. Therefore, in safety critical systems, we're going to have to use simulation more than we historically have done in order to show the properties in these open environments. Early on in that development process, and we're always trying in systems engineering and system safety to front load the left-hand side of the life cycle as much as we can so that we don't have to do rework. We're probably going to have to use synthetic environments in order to do that. And you're right, the other part that it can do is potentially to help us fill in the gaps in our data that we're using to produce the ML model. So if we've got a synthetic environment that we can take data out of to augment our data set, then that may be appropriate. Of course, at that point, you're going to have to make a safety argument. Well, you're going to have to put at least a confidence argument in as to why you believe that data is sufficiently good to contribute well towards the capability of the ML model, rather than persuading the ML model of something that's not true in reality. And that's where we're getting back to the potential for a hazardous internal system state, where the state of the world as understood by the system is different to the real ground truth that's out there. And one of the assurance elements is to show that gap is sufficiently small and you can be as confident in that as possible. Of course, if you've used a lot of synthetic environment data within that, you've now got to show the gap between that synthetic environment and the real world environment. And that's another challenge in its own right. Does that help you, Tom?
Yes, thanks, Mark.
We have another question, Mark, from Vishnu Vardhan Dadi. How can we see, or can you talk to the relation between safety and reliability when it comes to machine learning?
Okay. So there's two. we had a 2-hour debate on that the other week. So that was. I'm going to try and paraphrase it in the next 20 seconds. Okay, so we're talking ML components. The ML model must, of course, in some way be placed on hardware. And so the reliability of the hardware, which the actual final model is instantiated onto, is important. Rather like software, it's the final model, the failure characteristics against what we need, the intent, will be systematic errors. Every time you hit the same environmental condition, because you've got a particular model, you get the same wrong output against the safety characteristics. So in that respect, reliability doesn't mean much the same way it doesn't mean much for software logic. However, when you put this thing out into operational use, the reliability figure basically tells you something around the proportion of time that the ML component, or the system the ML component is embedded in, has been able to produce good results in its operating environment. So the operating environment is throwing random things at it, and it is trying to cope with those and do appropriate work. So you can, rather like people have software reliability metrics, if you look at those, they're all reactive measures. They're all looking at what you've actually managed to achieve in operation, rather than trying to predict it. And currently, we're not convinced that you'll, rather like with current software, you'll be able to do prediction of reliability well, except possibly for the hardware on which that ML resides. And therefore, it's going to be a reactive metric, not a proactive one within that. So it still works for hardware, but ML is a bit like software in terms of its link to reliability.
Thanks, Mark. We have one more question, or time for one more question from Duncan Greer. Have you had any engagement with regulators in the aviation domain, and how have they responded to your approach?
Yes, we're forever talking to regulators. You know, we need a set of regulators that has an understanding of these things in order for them to make a judgment in their certification processes. Yes, it's been pretty positive. You know, civil aerospace does certification over things like CS 251309 and the AAIP. They're currently looking at how to extend that to have these components in it. And yeah, we're talking to people like EASA around these. They seem to be pretty responsive. They know the challenge. They're trying to understand what that actually means in terms of what they're looking for as well. And so far we've had pretty good feedback from them. It's still an ongoing process. It got clobbered a bit by the pandemic because you couldn't meet in person. But that is one of our core aims, is to make sure that we have regulators on board. So we have contacts into that. The one that we've got the most at the moment is the UK's NHS regulators, the digital health people in the UK who accept medical devices into the NHS. And they're looking very assertively at the moment on using AMLAS as their basic process for doing that, and how that might be instantiated for them.
Brilliant. Thanks, Mark. Really interesting seminar. And I just want to thank you from the Centre's perspective for your time and effort on this. We will draw it to a close, but before I do, thank you to the audience for the interesting questions. I want to bring to everyone's attention that there are links in the chat to the example video that Mark has talked about, and also to a survey. So please fill that survey in, just give us some feedback on the seminar itself. Finally, if everyone can join me in thanking Mark for the time, and you can do that through the reactions button down the bottom. Thank you.
Great. Thank you very much, everybody.
Good night, everyone.
Good night.